So welcome to my talk. I'm going to talk about the results from my master's thesis where I implemented and proposed new Clang-tidy checks specifically for OpenMP. And yeah, first let's talk about how Clang-tidy works. Let's say we have a translation unit, then Clang-tidy will use the Clang libraries to pass that into an AST, which would look like this in our case. And then Clang-tidy will use AST matchers to define what it's interested in. For example, we want to have a function declaration where the first parameter is named x. This would generate one match in this translation unit, and the Clang-tidy check could then issue a diagnostic if it's an interesting problem that it's trying to diagnose. So there are three different kinds of matchers. There are node matchers, which only match AST nodes. So for example, a function declaration is an AST node. Then we have traversal matchers if we want to express some relationships between AST nodes, for example, has parameter, or if we want to know the type of a parameter, that's a traversal in the AST. And finally, narrowing matchers to say we want to constrain some property of an AST node or of some other part to say, for example, here it has to have the name X.
Should we pose questions right away or
Could do right now, but record the screen. Oh, you're doing that. Oh yeah, okay.
just a quick question.
The index, the zeroth parameter. This also has any parameter, which would check if there exists any parameter that has that. So very quick intro. Let's dive into OpenMP and why we need some checks. Parallel programming extra complexity, I think that comes with the territory. And the problem is that developers may introduce correctness issues, for example, data races, race conditions. We have maybe readability issues. Maybe it becomes hard to understand what's happening in the OpenMP case. For example, there could be some implicit behavior that we might want to make explicit, for example, data sharing, which also could help with correctness. And then we have performance issues which could be introduced. So yeah, there are a few things we can take a look at. And on the issue is that all of that can be costly to find later. If we have a data race, then some calculations can depend on that value that was calculated, and tracking where the issue is actually coming from might become very costly. You might want to enable a thread sanitizer, but then you have to rebuild your application and run it and actually hit that data race, and so on. And so we want to do all of that preferably as early as possible. So why not do that in Clang-tidy, a static analyzer which you can run in your IDE as well. So let's just have a random example slide where we have this application where we have an average coordinates function that's very interesting to us and in our hot path. And let's parallelize it with OpenMP and look on the internet how to do that. And we slap some parallel for on that, and reductions are cool, let's do that. But now we have a data race in line 15 on YSum, and that's because by default and implicitly all variables are shared, and so we are modifying a shared variable with multiple threads, and we have a data race. Now there's one check in Clang-tidy that already exists to help a little bit with that, or at least make it a little bit more obvious. That OpenMP use default none, which tells you to specify the default none clause. So that would mean that no data is implicitly shared anymore, and you have to explicitly say, I want this data to be available inside of this OpenMP directive, and it's either shared, it's private, or something else. And if we do that, now we have this default none, and we have to explicitly say which variables are shared. But now we have a compile error because we are accessing in line 15 YSum, but we didn't declare it as shared, private, or something else. So we got a compile error, and now it's obvious. Previously we had a data race in this case, and we would need to change something. we can either make the variable shared and add maybe an OpenMP atomic, but the most performant version would be to just add the reduction like we have on top. Yeah. Now this code is correct, but we can change some more, do some more changes to it and improve performance and a little bit of maybe readability as well. First up, something that's also an optimization pass in LLVM is merging parallel regions. And because it's an implementation, and because it's an optimization pass in LLVM, it's of course not really portable, and it depends on the implementation. Does it always merge these regions? Is there some threshold? And we can just be explicit instead and just do it ourselves. It becomes a little bit more readable because data sharing clauses are just only, we have one at the top, and we have only OpenMP 4 now and no OpenMP parallel 4 with all these data clauses. So a little bit of improvement in readability, but the real important thing is that we've merged these regions, made it explicit and portable. Next up, if we don't specify a schedule, it's implementation defined. It's hopefully mostly good, but why take the risk? Let's just write what would be the most optimal case in the most optimal schedule in our case. And here we have iterations where the workload is basically the same. So we can just use static without a chunk size, just divide it and run it. And finally, another optimization that also has an optimization pass in LLVM is removing unneeded barriers. And in our case, we have these two for loops, and their results are independent of each other, or their calculations. So we can remove the implicit barrier and have threads execute. If one finishes execution of the first loop, it can continue with the other, while other threads are still executing, for example, the loop in line 11. So we have removed barriers that are not necessary, and yeah. So that's basically the direction that all of this should go in, and I've proposed in my thesis for this 22 new Clang-tidy checks in the categories correctness, performance, and readability. And of those 22 checks, there are 15 that are somewhere between partially and fully implemented. Yeah, the rest are not implemented at all, but yeah. So first, let's take a look at the correctness checks that are available. There are 11 of those, and the two I've highlighted in blue, I'm going to talk about and show you the implementation a little bit as well. And there are quite a few of these implemented. There are a few that are not implemented and some that are partially. The partial is a very broad spectrum from it's missing a lot to it's basically finished. Yeah. Now for performance, I'm going to show you the implementation defined unroll check, which is also which also can have implementation defined behavior on the unroll directive. And there are a few more that I haven't implemented and not going to show, but maybe for some of these checks, I'll show you some diagnostics if they are implemented, just so you can see like what that would look like. And finally, readability checks. There are just 3. It's the smallest category, and yeah, I'm not going to go into detail into one of these checks. So implementation defined unroll. The idea is that the OpenMP standard defines 2 of these cases as implementation defined. So if you just say OpenMP unroll, but don't say if it's full or partial, that's implementation defined. And if you say it's partial, but don't say at what factor it's partially unrolled, that's also implementation defined. So let's just warn about it. And the implementation is relatively simple. It's only using AST matchers. And if we take a look at the AST matcher reference, we can see there's basically no AST matcher that we can use because almost none almost no AST matches exist for OpenMP directives. There's only one for the OpenMP directives base class basically, but not for any specific directives. Yeah, so we have to define our own. And to do that, we can define these. We need these three OpenMP directive matchers. So we have the OpenMP unroll directive, and then two clause matchers, the partial and the full clause. And this is basically the machinery behind Clang-tidy, where we have these matchers that we are defining. So here we have three node matchers for AST nodes, and we have one narrowing matcher just to check if we have an unroll factor. And to implement this, we have a register matchers function where we register what matchers we have, what is interesting to us, what are we looking for. And we have two of these in our case. First, we're looking for any unroll directive that doesn't have a full or a partial clause. And we add that to the matcher finder. And we have a matcher that tries to find any unroll directive where we have a partial clause present, but not an unroll factor. And depending on what we match, we want to issue a diagnostic for these different cases. And this would look like this, a lot of code, but it's quite simple. We just take a look at our result. Is there an OpenMP partial clause? So the unset partial is what we bound our node as. So if we have here, we want to say we want to match unroll directives with a partial clause, but that don't have an unroll factor. And this binding basically says save this as a node in the result map. So this is what we want to take a look at. This is what we want to take a look at, what we want to diagnose, for example, the location of, and that's basically what we're doing here. We take a look, is that present, or are we in this case where the partial doesn't have a factor, or are we in the other case? And depending on which way that goes, we issue a diagnostic. The implicit unroll factor of the partial unroll is implementation defined, and just tell it that's the location, highlight the source range. And in the other case, and we return if that's the case, and in the other case, we issue another diagnostic for the different case where we didn't specify a full or a partial. So that's basically the implementation for the implementation defined unroll issue. And that's what the diagnostic would look like on the example code I showed you earlier. We have one where we didn't specify partial or full, and that's in line 5, underlined here, OpenMP unroll, but there's nothing behind that. And then we have also a node that tells you might want to add a full, or you want to specify a partial unroll, basically telling you what the solution would be. And the other diagnostic would be that the implicit unroll factor is implementation defined, highlighting the partial keyword here. And that's that check.
You mentioned that there is no real AST metrics for stuff.
Yeah.
Could these be like automated? So are these metrics mechanically enough that you could just, in case you were to generate a parser for the open construct and policy server, you could also just generate a bunch of measures that would match the construct, or are these measures still something that they are meant to be more like semantically driven?
The AST nodes themselves are generated from a def file, I believe. So you could just take that file and generate the matches from that with macro magic stuff. So it could be possible to basically generate for all of the existing AST nodes these matches, but traversal matches would be hard because you would need to, for example, I don't know, get some clause from something, you would that to generate that would be a little bit harder, but you could do some of that automatically. But the AST matchers themselves are basically defined by hand right now, and there are documentation attached to these definitions, which show up in the AST matcher reference, which is yeah. So the AST matcher reference has all of these specified. So if we have an atomic cast expression, then we have a little explanation. And if we generate that automatically, we can't have examples there really. But yeah, it could be done in some way. Yeah. So for the next check, critical section deadlocks. So critical sections are basically regions where we lock some sort of lock, let's call it. And these critical sections can have names attached to them. So critical section parentheses A would be the critical section named A. And if you have multiple of this name, then they all basically denote the same critical section. So if you have in one function critical section A and in another function critical section A, these are basically global identifiers for the critical section A, and they are mutually exclusive from being executing their statements. So one issue we have, which is very simple, if we were to enter the same critical section twice, we can't do that. We would be waiting indefinitely for ourselves to exit our critical section before we can enter the critical section, which is a deadlock. And Clang doesn't warn on this, but GCC actually errors. So adding a check for Clang-tidy, which also has some additional capabilities. So GCC would only error out if the critical would be written right here, where we call this function. But with this Clang-tidy check, we can also traverse the call graph if we can. So if this function body is available to us, we can just go to that function body and continue our analysis. And doing that in Clang would become very costly very fast, because Clang and warning should be very fast, low overhead, and this basically goes almost into a static analysis territory, so Clang-tidy would be the better fit here. A similar issue comes up if we have a barrier, because a barrier states that all threads must reach that barrier, and only then we can continue execution. But if we reach a barrier inside of a critical section, then we can only ever reach that barrier from inside that critical section. Now we could have the barrier somewhere outside, but that would become very weird very fast. So just warn on that. And actually Clang would error in this case if we were to write it right here, but if we hide it behind this function call, then Clang doesn't check that. Now for the actually interesting part of this, if we have critical sections with different names and we are entering these critical sections in a nested way, so we have critical section A, then we enter critical section B inside of that, then we could very fast come to a problem. And that's because this is basically the dining philosopher problem, where the order in which we enter these critical sections is not very consistent, and we don't have a partial order where the ordering of entering these critical sections basically excludes any deadlock from happening. So here we have A, then B, but we have also B then enter C, and we have C, then enter A. And this is a problem because if we have 3 threads, one is in line 4 and has entered critical section A, one is in line 8, has entered critical section B, and one in line 12 for C. then the thread in line 4 will wait for the second thread because it wants to enter critical section B, but that can only happen if thread 3 has exited critical section C, which can only ever happen once thread 1 has entered critical section B, and so on. So we have a cycle. And that's basically the issue we want to detect. And to do that, we have to find the parent and child dependencies. So here, for example, A, then B would create this dependency from A to B. This the parent, then the child. And then we have the same for the others. And this apostrophe basically means it's the same critical section name, but it's a different critical directive. So B and B are different directives, but they're the same critical section because of their name. And after that, after we collected all of this, we can do depth first search on this and basically attach the parent-child dependencies where the name matches. That would be these dashed lines here. So we have A. If we were to start our traversal at A, then we go to B, and then we look for any critical section that starts at B, and we have one of these, and we continue our path until we find a cycle, which would basically tell us the ordering for how we enter all of these sections is not really consistent, and we could have a deadlock in this case. Now, in our case, this would be the diagnostic that would be generated. So the inconsistent dependency ordering for critical section A can cause a deadlock, cycle involving 3 critical section orderings detected, and it tells you also the cycle that we have. So A, then B, then C, then A. And it also tells you which the suborderings are. So the suborderings are basically what a thread could be executing. So A, then B, that's basically one thread that could be executing here, another thread here and here. And that's what's making up our cycle. Just to give you a little bit more information. And this is also where we would have, for example, if we didn't have A, then B directly, but that would be hidden inside of a function call, then we would get a basically call graph that would backtrace our path we take through the program. And to do all of that, we are not really going to use AST matchers, but another facility which can provide a much more flexible way of analyzing the AST. That's the recursive AST visitor. And before that, let's define some types. We have a call stack. We have critical section info, which is basically the critical section and the call stack of how we reach that critical section. So is it nested in some function call or not? And then we have the node map, which is basically critical section info, which is the parent, and then all of its children that it can reach. And as I mentioned, we use a recursive AST visitor for this, which is by default doing post-order traversal on the whole AST. And what's the important thing about recursive AST visitors is we can change how the AST is traversed. So we can basically, when we encounter a call expression, so we're calling a function, we can actually tell it, when we encounter the call expression, traverse the function body now, and we can, for example, push on a stack that we're traversing this function declaration, and in our case, that would be our call stack. So how would this look like? This is relatively straightforward. We have this traverse OMP critical directive, and that's basically called every time the every time the visitor finds a critical directive, and we just check, is there a critical in our stack? So are we a child of some critical? And if we are, then let's save that in our map. So we take the last critical section and add ourselves to its children. And if we've done that, then we can push ourselves on that stack, traverse the critical section, which basically means we are traversing the statement that's associated with that. So we have, in the example, we had OpenMP critical A, then we have critical B. So this would traverse from A, we could go to B, and then down to the x equals 1, I think it was. And that's basically the thing that AST matchers can't do. You can't really do this whole stack-based approach. Yeah.
You run into the same problem that you have limited access to OpenMP traversal facilities with the AST visitor, the same as you have with the matches?
No, because the so the recursive AST visitor has all existing OpenMP directives. So all OpenMP AST nodes are in the traverser. It's just the AST matchers that don't have them. But there's another problem, but anyways. So that's basically the basic thing we are doing. Then there are two more things we have to do. One would be the call stack traversal. So if we find, for example, an operator call expression, for example, a lambda has the function call operator, then we take the declared function at the top and see if we have the body available in our translation unit, because if it's not available, we can't traverse it. And if we have one available, we check, did we already traverse this call operator? Because if we have a recursive function, this would basically run Clang-tidy indefinitely, and after some time it will hopefully run out of stack, but who knows when that will be. And then we have to traverse the arguments, because the arguments to function can be function calls. So we have to, because we are overriding the traversal of this function call quite a lot, we have to do much of it ourselves. And in this case, we have to traverse the arguments. And finally, we push onto the call stack we are maintaining and traverse the body. So yeah, that's relatively straightforward. We're just changing how the recursive AST visitor, normally it would just see the function call, traverse the arguments and the callee, and then move on, but we need it to traverse the body as well. So that's what we're doing here. And another interesting thing is, if you write a lambda, it will traverse the body because you wrote the lambda, you want to know what's inside the body. And in our case, we actually don't want that, because when we encounter a lambda, we don't know if it's actually executed at that point. So we want to let the traverse CXX operator call expression handle all of that. And instead, when we see a lambda expression, we don't actually care about it, except for the initializers, so the lambda catchers. If we initialize a capture with an expression, then we care about it, because that would be executed when we encounter the lambda. Yeah.
Do you have like a CTOR constructor that takes a lot, has a critical section here, like an implicit CTOR? Would you capture that with the traversal you have here?
Yeah. 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 But what's not pushed is member expressions. I haven't pushed that update to my branch yet, so but yeah, that's basically copy paste of this. So I mean, the implementation is exactly the same. It's not just copy. Yeah. Yeah. After that, that's basically all we need to do in our visitor. And to use our visitor, we just declare it in our check function and say traverse the statement at which we start our analysis. In our case, an OpenMP executable directive, which is basically any OpenMP directive, but I've constrained the directive in the register matchers function a little bit to be a little bit more interesting to us. So this step is basically only doing this. We try to find the parent-child dependencies, And afterwards, we need to check if there are any inconsistent orderings. So I'm using depth first search for this, and it's a recursive function. And it technically isn't really work efficient, but given the amount of critical sections you hopefully would encounter during an OpenMP function, this should probably be fine. But if someone files an issue, that's for that. Yes. So we have all of our parent-child dependencies, and we want to turn them into this. So we're basically, I'm not actually creating a graph. I'm just traversing the basically implicit graph from these edges, and via connecting their names if they have the same name, and to finally check that there's a cycle. And to do all of that, we have a recursive function. We check if there are any nodes in our path. So if we don't have anything in our path, we are done with this recursive call. It's just recursion. Yeah. Now for what we actually need to do is, for all of the nodes, we need to find those that we can attach to our path in the depth first search. And that's basically, we take the name of our critical section and compare it against the last edge's name. And if they're not the same, we don't care about it. It's basically, we have A and B in our path, for example. And then we only take a look at those that have a B at the front. And yeah. Let's just move that at the top, cut out the if to fit the rest on the slide. And this is basically all the analysis we need to do. That's right here. For all of the children, we check if we have a critical section inside of the path that we have traversed that already exists. So basically, this checks if there isn't a partial order. If there isn't a partial order, we already visited it, and yeah. Now, if we didn't find a cycle, we can just add this the parent and our child to the path and continue the recursion, which would be here. And if that's not the case, we would start diagnosing this issue, creating this pretty diagnostic I showed earlier, which is the rest of those 100 lines that are missing at the bottom to generate this. It's basically just vectors and string concatenation and all of that. Yeah. Now, one important thing to note is, if we have the cycle, Clang-tidy can't really know where the cycle should have ended. So I'm actually generating this thing 3 times. One for each member in the cycle. So one for A, one for B, one for C. It's basically screaming at the developer, but we could, in theory, combine them into one, but that would mean, where do we actually issue the diagnostic, at what point? Because we would have to decide at what critical section do we generate the diagnostic. Would it be A? Would it be B? And that could mean that this issue falls under the radar. And if one of those actually starts somewhere down in the call stack, very far away, then that's even worse. So I'm just letting this thing generate all of the diagnostics, and yeah. Yeah. No, unless you're doing a Unity build. So Clang-tidy basically only works on one translation unit. There was some work to make Clang-tidy cross-translation unit capable, but I've never seen anything afterwards, so it's probably an abandoned project. Yeah. Now these 2 checks are basically finished. Now for the one that's quite not finished, there's a lot of it missing because it's basically the biggest check I've implemented. It's the unprotected shared variable access, which is basically a data race checker, but static analysis instead of, for example, dynamic, for thread sanitizer, for example. yeah, so there's a lot that's not implemented that I did propose to do. There are a lot of bugs still, and yeah, and also drawbacks that I specifically chose, and some specific ways I chose to do things, which means we have some drawbacks here as well. Yeah. So to do all of this, we need to do three things. We need to track which variables are shared, which are reductions, dependent, or some other property we are interested in. And we need to check if that access is protected, and protected is very hand-wavy in this case, to check if protection is correct for some of these uses. I actually defer from this check to another check, actually multiple of those. For example, that critical sections, if you have critical sections that are protecting some variable, but they have different names, so there's actually no protection happening. There's another check for that. So this check should be is a little bit more forgiving and might produce false negatives because of that, but it shouldn't also be like a very huge check which takes up almost all the execution time. So that's basically the idea behind all of that. And finally, we need to detect what are the modifications, because just because we're accessing a shared variable, that doesn't mean we have a data race there. The data race only happens if we access shared variables and one of those accesses is modifying. So that's what the third thing we have to check for. And to do that, we're using recursive AST visitor again, and using stack-based approach. So if we encounter, for example, this parallel, and we say value is shared, then onto the stack we push that that value is declared shared. And if we encounter a reduction, then we say, okay, this reduction is a modification of the variable, and so the reduction itself is a modification, but inside of the associated statement, so that's the for loop below, the variable value is no longer shared. It's in this case, it's private for each thread. And so we push onto the stack that this variable is private. Now the issue in this example, which is why we have a data race here, is the no wait. And that's because a thread that participates in this reduction, which modifies a value, can have finished its iterations, continued to line 11 and access the variable value, but another thread could still be reducing on top here. So we have a potential data race, and a diagnostic is issued, which tells you do not access shared variable value of type int without synchronization. It tells you where the unprotected access is happening, and also where the value was mutated, which is on top here in the reduction. If we remove the no wait, then no diagnostic is generated anymore, because now we have the implicit barrier here. And that means that any thread that is executing this OpenMP4 is waiting until all of the threads have finished this reduction. And so all will continue here, and no one is still reducing on value here. And these two are basically different. Because of this barrier, these two sections are basically different epochs, which is what I've called them. So there can be no thread here and here at the same time. One thing that's only proposed but not implemented is shown in this example. Here we have a function called A and B. And A and B are passed as non-const references, and the mutation analysis basically says, okay, you pass this as non-const references, this can be mutated, and I'm done. But we could extend the analysis to check if the function actually protects these accesses. For example, here, variable A is just incremented, and here we have variable B, which is incremented inside of a critical, which can be then considered a protected access. And to do that, we can check the definition of foo, and basically define a mapping of that function to say, okay, the variable, the function parameter A is not protected, but variable B is protected. And if we encounter the call expression at the bottom, we just take the callee, map our arguments, and say, okay, A is not accessed in a protected way, but B is. And then we would only diagnose this A as unprotected. Now for the limitations or the basically design decisions, any existence of a depend clause for tasks, for example, is considered enough. It doesn't matter if it's correct. There's another check for that, actually 3 of those. So there's a lot of checking for that, which this check then doesn't have to do. There's also the existence of, for example, critical or atomic clause directives, which are just considered to be protected. That's enough for this check. There are different checks to verify all of that. I think 2, maybe 3. And the actual real drawback is that all buffer accesses are ignored, because that would basically mean I have to do symbolic execution for offset stuff and maybe map out some iteration space. So that's basically absent at all, completely from this check right now, but that's maybe some future work to be done. For the implementation, very high level E, we are basically doing a very similar thing we have done before with the critical sections. Now we're doing this with anything to do with shared variables, is it a reduction, and so on. So we just check, are we in a parallel directive? If yes, then I increment this context depth. That's because the analysis for checking if a variable is mutated or not is very expensive. So we don't want to analyze the whole program and all of its expressions if it mutates some variable. We only want to analyze those that we care about. And that's also we can ignore some other cases as well with this. Now for the actual part of the implementation, if we have, for example, task weights or barriers, then we want to create a new epoch. And in the case of task weights can actually have a depend clause present, which means that the task weight only applies to tasks that specify a dependency on that variable. And so this would only create a new epoch for one of these variables and not for all. And if that's the case, we can return true. If it's a standalone directive because it doesn't have a statement associated with it, it's not, for example, an OpenMP4 that has a for loop, it's just a barrier. It doesn't have a statement associated. And what we do next is handle reduction clauses, because what we specify in the reduction will be mutated, so we mark those as mutations. And now we can go on to change a little bit of the traversal that we want to do, because when we traverse an OpenMP directive, we want to save, we want to change the state stack. So if it's a parallel directive that says this variable is shared, then we need to push onto the stack, this variable is shared. And we do this in lines 13 to 16. With this state thing, there's shared variables, private, reductions, are they dependent, and some more. And that's basically how the tracking for inside of these, for example, the reduction clause, which privatizes the variable, that's basically how this happens right here. Next, if that statement had a barrier at the end, OpenMP4 has a barrier at the end, we execute, we create a new epoch as well and continue execution. Now for the actual analysis, that's basically only the tracking for shared variables, reductions, and so on, and so on. For checking if a variable is mutated or not, we take a look at declref explorer, which basically means a reference, or basically, if you write something that you've previously declared, then it's basically a declaref expr. It's a reference to a previously declared declaration, part of an expression. So, and here you can see the parallel context depth. If it's 0, we return because we're not interested to analyze anything outside of parallel regions. And now we need to check, start thinking about what do we actually need to look at. So if it's a thread local variable, it doesn't really matter because it cannot be shared. Log types, I've decided to ignore. Maybe there's some things I need to actually check for these variables. But if it's OpenMP thread private or if it's a thread local, we ignore those. Then there's a whole if condition to check, is it currently shared? Was it at some point dependent? Was it at some point shared? Is it currently private? Is it unknown? And so on. That will probably change when this check matures some more, but yeah. Also checking if it's a reduction variable. We can if it's a reduction variable, it's considered protected, and this protective condition is basically what's the condition we are checking right now. But there's a lot of more checks to be done or behavior to be changed there. So that's also a little bit hand wavy, the is protected condition. And finally, if we have an unprotected access that's either dependent, then we save it as a analysis result for unprotected dependent accesses. If it is not dependent, it's just an unprotected access. And if it's mutating, we save that it's a mutation. Now, the interesting thing here is, of course, how do I check if it's mutating? And it's basically only using the expression mutation analyzer, which is an already existing analysis in Clang, which we can just reuse. Now there's some try to ignore buffer accesses, which is what I mentioned earlier, that this check ignores all of those. But the analysis of mutations is basically only done by the expression mutation analyzer. And we just have to call is mutated on it with a statement, which is basically the statement that it analyzes for our declaref expression. Yeah. Now, because of now the expression mutation analyzer is very interesting because you don't have to implement all of that yourself. And the issue is that it's, or not the issue, it's the implementation is very heavily based on AST matchers. And it's also the analysis that's the basis for miscellaneous cons correctness, which is an existing Clang-tidy check. But the issue is it's basically one of the most expensive checks because the analyzer for the mutation is comparatively expensive to most other check implementations. So I've tried to exclude most cases I could with these, with the trying to ignore as much as possible, and the other previous, in the previous function, the exclusions, for example, I had as well. And for some extra bits, some more useful utilities, there's a control for graph available you can use, call graph. There's flow sensitive, which is a whole data flow framework, which is comparatively new, and there's only one Clang-tidy check that uses it, which had some issues with crashes, hangs, memory, and so on. But it's actually very stable right now, I think. Then the rest of the analysis folder, which contains control for graph reachability, dominators, expression mutation analyzer, and some more actual implementations for the Clang static analyzer, or at least the headers. And Clang-tidy also has some useful utils, AST utils, which would be some AST matchers, which are in addition to the ones declared in Clang. There's aliasing analysis, for example, if there is a variable that has a pointer taken inside of the function, which variable is that? Declaref expr utils, which you can use to say, I want all the uses of some, for example, parameter. There's expression sequence. If you want to know, is this expression always before another, or is it only sometimes before another expression? Then there's include inserter, because macros, and Lexa utils, because sometimes you have to go down to the token level and actually pass tokens for your Clang-tidy check to diagnose interesting locations or to insert at some specific location you need. There's also type traits, so is trivially copyable and something like that as AST matchers. And yeah, I think that should be it, I guess.